Hey everybody. So we are going to be starting our nuclear chemistry unit. This is one of my favorites, and I know I say a lot of them are my favorites, but this one really is, just because I think it's really fascinating and interesting. It's unlike a lot of what we've talked about before, and there's a lot of applications like nuclear power plants and nuclear weapons that we can kind of get a chance to talk about during this. So something to kind of wrap up the end of the class with. So one of the things we need to do before we get into nuclear chemistry, though, is review isotopes all the way back in Unit 1. And that's because nuclear chemistry, a lot of it is about radiation and radioactive material. And radiation and radioactive material actually stems from isotopes. So as a reminder, isotopes are when the number of protons and neutrons do not match. So it's essentially atoms of the same element. So same number of protons, remember, because if something has, like carbon has 6 protons, so whenever you have 6 protons, it's always carbon, but then the number of neutrons can vary, and that's where we get an isotope from. So up here I have written out carbon 12, I'm trying to use my pointer, there we go, carbon 12 and carbon 14. That is one way to denote that something is an isotope. That's one way to write it out. So these are isotopes of each other because they are both carbon, but they've got a different number of neutrons. And the way we know that is because of this number that's hanging at the end. And this number, if you remember, is called the mass number. And the mass number is the protons plus neutrons. So we're talking about carbon, okay? Carbon has 6 protons. Oops. Has 6 protons. And you know that because you could look at the periodic table and see the atomic number is 6. So when we're looking at carbon 12, if there are 6 protons and the mass number is protons plus neutrons, and 6 of them are protons, mass number is 12, there's got to be 6 neutrons. For carbon 14 then, to get to that 14, 6 of them being protons, there must be 8 neutrons. So hopefully this rings a little bit of a bell. So that's one way to write out isotopes, is with this carbon 12, carbon 14 method. We also learned a while ago about isotopic notation, which is another way to write it out. And what that looks like, and we learned this back in Unit 1 as well, you write the element that you're talking about. So we're talking about carbon, so I'm putting a C. And then in the bottom left corner, you put the number of protons. So for carbon it is 6. And then in the top left corner, you put the mass number. So for carbon 12, I would put a 12. So for carbon 14, what that would look like would be the C again, because it's carbon. 6 protons again, because it's carbon, and then I would write the 14 up here. So this and this is telling you the same piece of information, just written out in a different way, and same thing with this and this. So why don't you go ahead, pause the video for a second, try to fill out the nitrogen 14 and 15 really quick and see what you can do on your own. Alright, so these are the numbers you should have gotten. So you've got nitrogen 14. Nitrogen has 7 protons from the periodic table. So if it has a mass number of 14, there must be 7 neutrons. 7 plus 7 for 14. Nitrogen 15 must have 8 neutrons. 7 plus 8 is 15. And then this would be the isotopic notation for both of them as well. So remember, this is the mass number, top left, number of protons, bottom left. Another thing we learned about, back in Unit 1, was how to calculate the average atomic mass. So remember, atoms are super, super tiny, so like whenever you grab a hunk of carbon, these isotopes occur naturally. So when you grab carbon, there's carbon 12, there's carbon 13, there's carbon 14. And when you work with carbon, you don't necessarily know if you're working with the 12, 13, or 14 because they're so small and you can't isolate them. But the problem is carbon 12, 13, and 14 all have different masses. Because if you remember, the mass of an atom comes from the protons and the neutrons. So a carbon 14 atom is heavier than a carbon 12 atom. So in order to deal with this, we need to calculate the average atomic mass. So we do this with two pieces of information: the relative abundance of an ion and an isotope, and the mass of that isotope. So we kind of had a equation that we used. It was mass times Ra plus mass times Ra. So the mass being the mass of that isotope, Ra standing for the relative abundance. So looking at this one here, if there's 75.77% of chlorine-35 and 24.23% of chlorine-37, what is the average atomic mass? So when we plug in, so let's do this first one here. The mass is going to be the mass number, so it's going to be that 35 multiplied, and then remember whenever anything's in a percentage, and you're going to plug it into an equation, it needs to be in decimal notation, so you're going to go boom, boom. So you're going to plug in 0.7577 plus, now we're going to do the other one. So the mass for that one was 37 times decimal notation, boop, boop, 0.2423. So you'll multiply them, you'll add them together. When you do that, you should get 35.48. I did 4 sig figs because the mass numbers are actually exact, because it's protons plus neutrons. Protons is an exact amount, neutrons is an exact amount. Those are countable, and then the percentages is where the measurement comes into play. So I did 4 sig figs, so 35.48. And if you remember, the unit we did for this was AMU. And that AMU stood for atomic mass units. So essentially, the units that make up an atom's mass. So 35.8 is our final answer. And if you actually compare this to the value on the periodic table, it is very close. So there's some more review on this in the homework assignment if you want some more practice, but we did learn this in Unit 1 as well. So there are multiple things to discuss when it comes to nuclear chemistry, radiation, radioactivity, things like this. The first one we're going to talk about is decaying and half-life. So when this comes into play is unstable isotopes. So by unstable, I mean that nucleus where the protons and neutrons are, that combo of protons plus neutrons is unstable. That nucleus is unstable, and it would like to become stable. So we can actually call these isotopes radioisotopes, and that number is coming from that name is coming from the fact that they are radioactive. So unstable isotopes can be radioisotopes because they're radioactive. They emit radiation, and they do that by going from unstable to stable. And we can also call this decay. We can call this radioactive decay. So essentially, when the nucleus is going from unstable to stable, it's decaying, it's losing something, it's knocking some stuff off. That stuff we can consider to be radiation, and then it is now stable. We will go into more detail about this tomorrow, but I just want to throw the names out there so they sound familiar. So there's 3 different types of ways atoms can decay. They can decay through alpha decay. So an unstable isotope, if it's going through alpha decay, means when it wants to go from unstable to stable, it does that by emitting an alpha particle. And that alpha particle is a form of radiation. And we'll talk more about alpha particles and all that tomorrow. They can also go through beta decay, which means when it's going from unstable to stable, it emits a beta particle, and that beta particle is also another form of radiation. And then the last form of decay it can go through is gamma decay. So when it's going from unstable to stable, it is emitting gamma rays, which is another form of radiation. So like I said, we will talk about all 3 of these types of decay in more detail tomorrow. But the next thing we're going to talk about is going to be half-life, and you need to be aware of the fact that atoms decay, go from unstable to stable, to kind of get that part down. So the part of decaying, the part of radiation that we're going to be talking about today, is the rate in which radioisotopes decay. So one of the really important factors essentially on how radioactive a material is or how dangerous it could be or what it can be used for is how quickly it decays. So that process of going from unstable to stable, is it happening in a matter of seconds? Is it happening over billions of years? And the rate in which it's doing that really kind of determines a lot of its properties. And the way that we measure that rate in which it goes from unstable to stable is the half-life. Oops, that's not what I wanted to do. The half-life. So the definition, textbook definition of half-life is the amount of time it takes half of a sample of atoms to decay. And the atoms here are specifically those radioisotopes. So remember, atoms are super, super, super tiny, so you never have like one atom in front of you. You have billions of atoms in front of you. So this half-life is, if you've got a billion atoms in front of you, how long does it take half of those billion to go from unstable to stable? And remember, if they're going from unstable to stable, they're decaying something and they are emitting radiation. So the example I have here is, let's say you have 1 mole. Remember, 1 mole is at 6.02 times 10 to the 23rd atoms. So you've got 1 mole of carbon-14. And after 5,730 years, you now have 0.5 moles of carbon-14. So half. So half of it has gone, half of it has decayed. That would mean the half-life of carbon-14 is 5,730 years. So every 5,730 years, a sample of carbon-14 is going to reduce by half, and that half that's gone has now decayed. It's gone from unstable to stable. I've got some pictures here too, if you kind of want to visualize it. So this would be an example of, you've got all of them. So this is your original sample. You've got all of your radioisotopes there. None of them have decayed. And then after, you've got, and we're saying we have 100 here. So after 1 half-life, and that half-life can range, like for example for carbon-14 it's 5,000 years. There's some ranges and I'll show you that in a second. After 1 half-life, half of that 100 is gone. So those radioisotopes have gone from 100 to 50. And now, as you can see, there are 50 red dots left. After another half-life, the second half-life, another half are gone, and now there's 25. After a third half-life, another half of them are gone, and now there's 13, 12.5 sig figs. And it's going to continuously do this process essentially until infinity, right? Have you ever heard that thing where if you fold a piece of paper in half forever, like you'll never stop, right? You can always have something. You're never going to get to zero. And the idea behind this is because there's billions and billions and billions of atoms. Are we really ever going to get to zero or get to a measurable way of knowing there are zero? So that's why we're having it continuously. So notice what this is it's not half of an atom decaying, it's half of a sample. That's the key word. That's what kind of people get flip-flopped with this. It's half of the sample. So if you look at this, there's 100 here, now there's 50, now there's 25, now there's 13. So some of them are remaining, just some are decaying faster than others, and we're going to measure that by when they decrease by half. So now that we kind of have an idea on what half-life is, let's get into some more specific problems. So I have on here a chart with different radioisotopes. So as you can see here, they are written out in that isotopic notation. So these bottom numbers are the number of protons, and these top numbers are the mass number. Here are the different kinds of decay we talked about. The alpha, beta, gamma, don't worry about this right now. Like I said, we're going to do more of that tomorrow. But I want you to kind of see here is the range in the amount of time that half-life can have. So for example here, strontium-90 has a half-life of 29.1 years. So when you have a sample of strontium-90, every 29.1 years, half of the strontium-90 in that sample is going to decay, go from unstable to stable, and emit radiation. Look at this, uranium-238, 4.5 billion? Yeah, 4.5 billion years. So huge difference there. We've got, what is this, carbon 11? 20 minutes. So there you can have a huge range of how quickly some of these things are going to decay over time. And what's interesting is if you know one of two things, you either know how much sample you originally had, or if you know how much sample you currently have, and if you are aware of a radioisotope's half-life, you can then solve a bunch of different problems. So let's go ahead and look at some of those examples right now. So for this first one up here, we have polonium-218 has a half-life of 3 days. So remember, every 3 days, half of the sample decays. If there were 12 grams originally, how much is left after 6 days? Okay, so we currently have 12. Half-life, 3 days. How much is left over after 6 days? So there's so many ways you can do this. Please have the flexibility in kind of doing what you want to do. I do want to see work like I always do, just because I want to make sure you didn't just get the number out of nowhere. I'm going to kind of show you what helps me. So I'm saying, okay, I've got 12 grams to begin with. Half-life 3 days. So after 3 days, so that's a half-life, right? After 3 days, I know that this would decrease by half. That's what that word half-life means. So now I would have 6 grams. Okay? My question, though, was 6 days. So if I did another half-life, if another 3 days went by, then that would go in half again. So now I've got 3 grams. So 3 days plus 3 days, there's my 6 days. How much would I have left? Well, I would have 3 grams. It would half twice because 2 half-lives would go by because the half-life's 3 days and it asked for 6. Let's look at another one then. Carbon-14 has a half-life of 5,730 years. If a 2,000 gram sample has decayed for 17,190 years, how much of it remains? So for this one, what we're going to start off with now is the 2,000 gram sample. So in this case, we know we had 2,000 grams, and now we know the time that has passed. We know this much time has passed. So we want to know how much would be left of the 2,000 grams after this amount of time. So it's a similar setup. So now I'll still start with the 2,000 grams. All right, and then each half-life, we're told, is 5,730 years. So after 5,730 years, right, because that's one half-life, the 2,000 will cut in half, because a half-life is the time it takes half of it to go away, so that'll be 1,000 grams, okay? Now the goal is to get to 17,190. We're not there yet, so we'll go again. Do another 5,730 years. And now we're down to 500 grams. If I add these together right now, we're still only about 10,000, not quite there, so we'll do it again. 5,730. Now we have 250 grams. And if you were to add all of these up, so 1, 2, 3 half-lives, that would equal the 17,190 years. So your answer would be 250 grams. I promise the numbers will always work out easily. Like, you're not going to have to do any weird fractions. It'll work out nicely where all of these 3 added up equaled exactly that number there. All right, so now I want you to try this one on your own. So a sample of cobalt-60 has a half-life of 2.5 days. It currently weighs 100 grams. What was the mass of the sample 10 days ago? So you try this one. All right, so the final answer for this one then is 1,600 grams. So we were told that the half-life was 2.5 days, and it currently weighs 100 grams. So now we know that every 2.5 days it halved. So if we go back in time, 2.5 days ago, it must have been double what it currently was. So 2.5 days ago, it must have weighed 200 grams, since after 2.5 days, it would go down to 100. Another 2.5 days ago, it was 400. Another 2.5 days ago, 8, and then 1,600 grams. And then this 2.5 plus 2.5 plus 2.5 plus 2.5 is equal to that 10 days ago. There are a lot more examples of this on the 10.1 homework as well, if you would like some additional practice. So where half-life can be really useful is in the process of radiometric dating. So maybe you guys have heard the phrase of carbon dating before, or maybe you've wondered why we know some rocks are billions of years old if we obviously weren't around a billion years ago. So we can do this by this process of radiometric dating. Essentially, those half-life problems we just did, we can apply the same thing to real-life materials. So for example, if we find a rock in the ground and there is, let's use the uranium-238 example. If there is like 5 grams of uranium-238 in this rock, and I know that through the process of making this rock, that generally it's made with 50 grams, right? I'm just throwing out numbers here. Then we can use that same process and say, well, 4.5 billion years ago, it must have weighed 10 grams, et cetera, and they can date that way. So the idea of carbon dating is actually using that carbon-14 from that previous problem, which had that half-life of 5,730 years. So essentially, carbon, as we now know, is an organic molecule. Like, we're primarily carbon. Every living thing is primarily carbon, including like trees and plants, things like this. So we have some carbon-14 in our bodies. Even though it's radioactive, it's fine, but we do have carbon-14 in our bodies. So when we die, what can happen is, since our body stops getting new carbon-14, because we stop eating, obviously, they can actually they can give a rough estimate on how old or how long ago that object died based on how much carbon-14 is currently in it. And what I have on here is a link to a guy that I think does a pretty good job of explaining radiometric dating, so you can get some more information there as well. So at this point, you can go start doing the the radioactive decay lab. You're going to kind of get another visual of how this decay process goes and really what that definition of half-life is, and we'll go from there. So I hope you guys have a great day, and I'll see you tomorrow.